Hello, hello everyone. Good evening. Am I audible?
Yes, you're audible.
Okay, great. So, how was the quiz? Any feedback? Yes, anyone? Any feedback about the quiz? It is good, bad, okay, difficult, easy. No
Not
feedback.
bad. Not
Okay,
bad.
not bad. Okay. So, like few students have replied on discourse post, so they have mentioned that most of the topics are covered, right, from week 1 to 4.
Yeah.
Yeah. So, like in the quiz too, the syllabus is generally week 1 to 8, but we'll focus more on week 5 to 8. And in that also, week 5 and week 6 will be more important. So, you can expect around 50-55% weightage from week 5 and week 6 only in quiz too. So, please prepare accordingly.
Okay.
To, yeah. I hope I'm audible, right?
Yes, sir.
Yeah. Okay. Great. So today we'll start with the week 6 part, but before that, I want to discuss about week 5 concept because it is required for to understand the concept of week 6. If you are not understand what is there in the week 5, so week 6 will be very difficult for you, right? So I will start with the week 5 one question, one practice assignment question. I'll discuss that and then we'll start with the week 6 part. Okay. Yeah. So how many of you have watched the week 6? Just raise your hand. Okay, great. How many of you saw week 5 practice assignment? Okay. So is my screen is visible?
Yes,
Hello?
sir.
Yeah.
Visible. Visible.
So this is week 5 practice assignment question number 2. Okay. So I will discuss this question first and then we'll start with the week 6 part. So we have a relation R having A, B, C, D, E, F as an attribute, and these are the functional dependencies. Right? So first tell me what is functional dependency. If I said A determine B, what does it mean? Anyone? Okay.
A can
So,
be uniquely
yes,
used. A can be uniquely used to identify B.
yeah. So, for example, we have a comma b, and we say we have a functional determine b, right? So, if there is a1, then its corresponding value of b is if it is b1. Then for next set of a1, the same value should be there, right? So, it is not like if for a1 we are having b2 also. So, this will violate the functional dependency concept, right? So, this is about the functional dependency part in short. Now,
Can you please
let's
take an example, like what is
okay.
functional dependencies?
When I say A determine B, so A is functionally determine B, so it is B is dependent on A, right? So suppose if A1, this is A, this is B, we have one table here. Okay, this is A1 and this is B1. So if I said A determine B, right? Then the value of a1 is corresponding to that particular value a1 is b1, right? So then in the next set of the particular table the value of a1 must be b1, right? It cannot be a2, right? So it should uniquely determine each value. So a1 is determining b1, then a1 should determine b1 only, not b2, right? So A1, B2 we cannot write like this, because if it is there in this particular table, say A1, B1, A1, B2, then this functional dependency concept is violates, right? So A is not functionally determined B. Okay, let us take about this ABC now. So AB determine C. So the combination of AB uniquely determines C, right? So A, B, C. Suppose this is A1, B1, and C1, and suppose this functional dependency holds true in this particular table, right? So now the combination of AB uniquely determines C. So if now A1 is determining C1, I cannot it A1 B1 should not determine any other attributes as C2. So this should not happen, right? This is not allowed. So it will violate the functional dependency. But A1 B2 can determine C1, because A1 B1 and A1 B2 both are different things, right? Because the combination is different, right? A1 B1 and A1 B2. Similarly, it can be like this also, like A2 B1 also determine C, right? So on the right hand side it can be a duplicate value, but on the left hand side of functional dependency it should uniquely determine this particular attribute, right? That's the concept of functional dependency. So this the starting of week 5 thing. Okay, any doubt, anyone? Okay, suppose if I have this particular relation R and having this functional dependency, then tell me how to calculate the candidate key.
Sir, first we start with the attribute value which are not the in the right side of the functional dependency.
Okay, so first tell me what is key. Okay, what is key?
Which determine the relation
Attribute
R.
or set of attribute, and if it gives me all the element present in the R or all the attribute present in the relation R, then I can say this attribute or set of attribute is a key, right?
Yes, sir.
So for that, so suppose I want to check whether A is a key or not. So what I can do, I can take the closure of A based on this functional dependency and see whether I'm getting R or not, right? So if I take the A closure, I will not get R. Then check for B, then check for C, then similarly check the combination of A, B, then A, C, then A, B, C, right? Combination of 3 attribute, combination of 4 attribute. Like that you can follow. But the one shortcut we can follow is that first we'll see what are the attribute which is not present on the right hand side of any functional dependency, right? As you mentioned. So here what are the attribute which is not present on the right hand side of any functional dependency? C is
A,
present,
B,
E is present, D and F is present. So AB is not present on any right hand side of any functional dependency, right? Then A, B must be a part of candidate key, right? To verify whether it is a candidate key or not, what we can do, we can simply take the closure of this, that is A comma B or AB, right? Now what is the closure of A comma B based on this functional dependency set? AB
A,
will
B,
determine AB, right? Yes, go ahead please.
A, B, C,
Huh?
E,
Yeah, from AB I will get C, from A and C I will get E, right?
F. A from A, B we get F.
From AB I am also getting F, and
From
from
E, F,
I am getting D,
D.
right?
Yes.
So we are getting all the attributes present in the relation R, that is relation R, right? So AB is my candidate key here, right? So AB is my candidate key. Now, what is super key? Just tell me, what is super key?
Any attribute having A with AB
Yeah,
can be super key.
yeah.
Combination of candidate keys.
Combination of not candidate keys. Like if we consider the candidate key with any other attribute, that will form a super key, right?
Yeah.
So AB itself also super key. So AB is also super key, candidate key. But if I say A B C, A B D, right? A B F, these all are super keys, not candidate key. Only AB is a candidate key and super keys, right? So
Yeah.
A B C, A B D, A D F, any combination of with candidate key, any attribute will be a super key, right? That's the thing. Now this is about the candidate key and super key. Now what are the prime attributes and non-prime attribute? What are the
Prime attributes are which are present in any key.
yes, the attribute which is present in the candidate key, not any key, right? So
Okay.
attribute which is present in the candidate key, that those are the prime attributes. Here A and B are the prime attribute, right? What are non-prime attribute? Which are not part of candidate key, right?
Maybe,
So
yeah.
remaining, yeah. So C, D, E, F are my non-prime attribute, right? So in week 6, in every question, first you have to find out candidate key, and then you have to find out prime attribute, non-prime attribute, and then you can start with the question. So this is the basic thing required for a week 6 concept to solve any problem. Finding out candidate key and finding out the prime attribute and non-prime attribute, right? So this is most important step. If you are not practice enough to find out candidate key, prime attribute, then it will be difficult, right? Week 6. So please practice like how to find out candidate key, what are prime attribute, non-prime attribute. Okay, so these things are required, right? Okay, so that's it that I want to discuss from the week 5. That is how to find out candidate key and what are the prime attribute and non-prime attribute, right? And here for this question, like it is based on the decomposition. So suppose we have relation R. I am decomposing it into R1 and R2, right? So what is lossy and lossless? Yes, anyone tell me what is lossy and what is
If
lossless?
lossless is if we are getting relation R from the decomposition relation, then
Hmm.
it's lossless. There are three properties for a
Hmm.
relation to be lossless. Uh,
Yes. So for lossless, if I again join these two decomposed table, then I will get the same relation R, right? That is
yes, sir.
lossless. And here I will get some extra double or less double. That is lossy, right? Here I will not get. Here I will not get the same relation R. That is lossy. But to check whether it is lossy, lossless or lossless, there are three conditions for lossless, right? So first one is R1 union R2 should give me R, right? So
Yes, sir.
attribute of R1 union attribute of R2 should give me all the attributes in the relation R. Then second one is R1 intersection R2. So what are those common attribute present in the relation R1 R2 should not be an empty set, right? It means that
Yes.
there must be some common attribute, right? There must be some common attribute, right? Between R1 and R2 to satisfy this condition. And the third condition is R1 intersection R2 should give me R1.
R2.
Or
So if you compare condition 2 and condition 3, what we can conclude? Yes, anyone?
For any attribute in R1 or R2 is a key.
Yes, yes. So first thing is there must be some common attribute, right? Between R1 and R2 must be common attribute. And that common attribute must give me R1, R2, right? So it should be key, right? It should be key of R1 or R2. It can be candidate key, it can be super key or any key, right? So if I take a closure of any attribute, I should get R1 or R2. So if these three conditions are satisfied, then I can say our decomposition is lossless. Otherwise, it is lossy, right? So now just come back. Let us come back to this question. So let us check for first option. So first check R1 union R2 for first option. A, B, C, D, E, F, right? So my first condition is satisfied, right? This one. Then R1 intersection R2. What is the common between R1 and R2?
E and F.
E and F. Now whether this E and F will give me R1 or R2, how to check that? Just take the closure of EF based on this functional dependency set
EFD.
EFD, right? This is R1, right? So this is this condition is getting satisfied, right? So this is lossless decomposition. So this option is not correct. Now let us check for this one. A, B, D, C, E, F. So A, B, C, D, E, F. So first condition is satisfied, but there is no common attribute, right?
Yes, sir.
So this is lossy. So this one is correct. Now for third option, A, D, E, C, B, E, C. So A, B, C, D, E. F is not there. So this is lossy, right? Now D, E, A, B, C, F, B. So here A, B, C, D, E, F. Yeah. So first condition is satisfied. B is common attribute, right? Now if I take the closure of B,
B itself.
yeah, so B itself. So it is lossy, right? My third condition is not satisfied. So this one is also correct. Okay. So any doubt like how to find out candidate key, how to find out prime attribute and non-prime attribute, and how we decompose the table, how to check whether it is lossy or lossless.
No, sir.
Okay, great. So now we'll start with the week 6 part. Yeah. So in the week 6, we have normal form, right? So different normal forms, that is 1NF, 2NF, 3NF, BCNF, and then 4NF, right? So this first four deals with the functional dependency concept. This deals with multi-value dependency concept. So in the first lecture, like lecture 6.1, we have discussed about 1NF, 2NF, 3NF. Then in the lecture 6.2, it is BCNF. And lecture 6.3, I think there is case study. So you can watch that lecture. Then 6.4, we have discussed about MVD and 4NF, right? And in lecture 6.5, we have that temporal data relation. You can just watch that lecture. So today I will cover 1NF, 2NF, 3NF, BCNF. In the next session, I will cover MVD and 4NF. Okay. So this case study, simply you can watch the video, and this is also like just go through side, that will be enough. But these are the important for exam point of view also, and if you see like companies or in placement point of view, they will ask you question based on normalization concept, right? So that's the case. Now let us start with the first. So yes, so what is normalization here? Yeah, so basically normalization is, it is a schema refinement technique, right? Organizing the data in the database, right? So if we have whole relation are having say number of attributes, say 15, 20, 10, 15, like this, and due to this there will be a redundant data, right? Duplicacy of data, right? And also it will cause a different anomalies, like for insertion, update, deletion, it will cause a difficulty to update the value, right? Delete the value, right? If you delete one row, so may like corresponding value which should be required, that will also get deleted. So there are different anomalies, right? If we just keep the data like this only, if there is redundancy in data, right? To avoid those anomaly and to reduce the redundancy in database, what we can do, we can go for normalization of concept, normalization part, right? So you can see the goal of a normalization is basically to eliminate the redundancy, right?
So you are not audible.
Hello. Sorry. My Wi-Fi went off. Hello. Am I audible?
Yes, sir. Yes, sir.
Okay. Okay. So, is this was audible when I was teaching this one NF?
No,
No,
sir.
I don't know. Okay. This one.
No, sir.
This one also no. Array. This one. This slide.
So actually, you were on the first slide.
From first slide only. Yeah. Okay. I didn't notice that. Okay. Okay. So after that, this one was also not audible, right? It is not there. Okay. Uh, yeah. So we'll discuss about different normal forms. So about normalization, like it is just a technique to organize the data in a database. So basically, we have to. The main purpose of normalization is to reduce the data redundancy, right? The duplicacy of data, right? Because it will lead to an undesired characteristic like insertion anomaly, update anomaly, deletion anomaly, right? So basically, the goal of normalization is to just eliminate the data redundancy, right? Redundant data. So that's simply normalization part. Now here you can see what are different anomalies here: update anomaly, insertion anomaly, deletion anomaly, right? So say in this example you can see employee 519 is having a different address, right? Two addresses there. So if I want to update the address of this employee, so it may thing like this address also get changed, right? If I just want to update, so it will lead to a different anomaly and inconsistency in the database, right? So for that we need to go for a normalization thing. So this lossless decomposition property, like as we had discussed in the start of the session, like it should be possible to reconstruct the original table. So suppose we have relation R decomposed into R1 R2 like this. So if I just join this R1 R2 or any of the relation, all the relation, I should get the same relation R, right? So that should be a lossless joint decomposition property. Notice dependency preserving property. So there should be no functional dependency should get violated, right? So in this case, suppose if AB determines C is functional dependency in this relation R. So if you are normalizing till 3NF, so this dependency should get preserved, right? So this concept is covered in week 5, okay? Dependency preservation. So you can go through it. So this is about dependency preserving. Now we have different normal forms like 1NF, 2NF, 3NF, right? And here you can see a relation database is often described as normalized if it meets the third normal form. Why it is so? Because till 3NF we can ensure that our this functional dependencies get preserved, right? If we go for a BCNF, then it may or may not get preserved. So functional dependency may or may not get preserved in the case of BCNF, but till 3NF we can have a dependency get preserved. So that's why it's often described as normalized till 3NF, right? So if anyone asks about why we want to go for BCNF or what is the limitation of 3NF like this, like what is so in that case you can say okay, till 3NF we can ensure that dependency is preserved, but in the case of BCNF we may or may not get preserved, right? Dependency may or may not get preserved. So that's the thing. Now here we have different normal forms. So BCNF, 4NF, we will be focusing on these two things only. Just you can just simply go through it. So that's it.
Screen
Yeah.
is not visible. Is it only for me?
Hello.
Oh,
Huh?
okay. No, no, now it's okay, sir.
Okay. Fine. So what is first NF now? It is first normal form. So the relation in the first normal form when there is no multi-value dependency. So what is not dependency attribute? So what is multi-value attribute here? Here you can see in this particular table for S1 we are having C comma C plus plus, right? So this is multi-value attribute, right? We are storing two values in the same field, right? So if it is there, then there is MVA exists, multi-value attribute exists, and it is not in 1NF, right? So it will be difficult if you want to update a data of S1. So suppose if you want to change the course name to any other course, so it will be difficult to update that, right? So that's why it is not in 1NF, right? Now to avoid that, how to avoid the 1NF thing? Simply we can remove the multi-ordered attribute. Like how we can do that? Simply we can add one more tuple or row like S1A C++, right? So we have divide this particular row into row, right? So S1A C and S1A C++. Same for S2B C++ and S2B DB, right? So in this case, this is how we can uh, convert this particular table into 1NF by just simply removing the multi-valued attribute things, right? So the domain must be atomic here. So domain must be atomic, okay, and that is no multi-valued attribute. Then we can say it is in 1NF. So suppose in the question it is asked, relation is given to you. Suppose if you have mentioned domain must be atomic, it is fine. Even if you are not mentioned that domain must be atomic, then still you have to assume that domain is atomic, right? So you have to assume that domain is atomic for solving the different questions, right? Unless you have specified that in the question. So that is about the 1NF thing. Anyone, any doubt in the first normal form?
It is simple that you should not have multivariate
Yes,
attribute.
that's it. Yeah. So that is first normal form. Now once we remove that MVA, right? Then what are the different things that it costs? Like what are different drawbacks of that? So that's why we want to go for 2NF, right? So suppose same table we have expanded like SID, status, city, PID, and quantity, and we have this functional dependency. Here you can see SID determines city, SID determines status, right? Here you can see like this, and city determines status, and here SID PID combined determines quantity, that is SID PID combined determines quantity, right? So now this table you can see it is in 1NF because there is no multi-valued attribute, right? So domain is atomic. So here is no multi-valued attribute exists. So we can say it is in 1NF, right? But what are the drawback of this? Suppose if you want to delete this particular row, right? If I delete this particular row, then the data about that S3 lives in Kotak, that is SID determines city. This information get lost, right? If I want to read about this particular quantity, right? Also, like there is insertion anomaly that we cannot insert supplier S5 located in kernel. Say SID, that is S5 located in kernel, right? We cannot insert this in particular table unless there's at least one part, right? So that is quantity or PID should be there because key is SID and PID, right? So that's why insert anomaly causes, right? Similarly, update anomaly can cause. So in order to overcome this drawback, we can go for a 2NF, right? Because will redundancy in data, it will be too different. We can simply compose this two tables, then we can remove this type of anomalies, right? This functional dependency. So how to do that? Like how to convert 1NF into 2NF? That we'll discuss that. Okay. So yeah. So you can see like possible redundancies if left hand side is not a super key, right? So if left hand side is not a key, then it will have a multiple values, right? It can be a duplicate, right? S can be duplicate, so 1313, so it will lead to a redundant data, right? So if X is a key means it should have null plus, sorry, it should be not null plus unique constraint, right? In the database level, so it should be unique. So here you can see if X is a key, so one cannot be a repeated value, it should be unique, right? So that's why if left hand side is a key, then you can see like a corresponding value may or may not be duplicate, right? So this is the case. Yeah, so this is about the 1NF. Now here you can see there are different drawback, right? Now to overcome this, we want to decompose this table into 2NF, right? So how to do that? There are different conditions for 2NF. So what are those conditions? So first one is relation R must be in first normal form, that is no multi-valued attribute should exist, right? If it is 1NF, then we can check whether R contains partial dependency or not. If partial dependency is there, then we can see it is not in 2NF, right? So what is partial dependency here? So suppose in the earlier thing we have find out that AB is a key, right? AB is a key. Suppose AB is a key and we have functional dependency like B determine C. So this B is a part of candidate key, right? Part of candidate key, subset of candidate key. Then B determines C will be called as partial dependency, right? So suppose if we have relation R having x, y, a as an attribute set over R, where x is a any candidate key, y is a proper subset of candidate key, and a is a non-prime attribute, right? If y determine a exists in R, then R is not into NF if this condition is satisfied. So first one is y is a proper subset of candidate key, right? So here you can see this B determines C, right? So this is a part of candidate key. It is a proper subset of candidate key, right? If this case is there in the functional dependency, then we can say it is partial dependency and it will violate the 2NF condition, right? Also this C is a non-prime attribute, right? So if y determine A is there, if it is NPA and this is a part of candidate key, it is subset of candidate key, then we can say this is a partial dependency, right? So if partial dependency is present, we have to remove that in order to be in 2NF. Any question, any doubt? Yes, Priyanka?
So this partial dependency that you explained, can you tell me in context to the example, because I'm not very clear about the two
Okay.
conditions that you explained. Yeah.
So at the start of a session, I have discussed one example, right? So we have one attribute R where A, B, C, D, E is the attribute, and we have functional dependency set. Say A, B determine C, B determine D, and D determine E, right? And if we calculate here CDE, AB is a candidate key, right? So AB is candidate key, right? Once you find out that AB is a candidate key, now check for other functional dependency, that is B determine D, right? Whether B is a part of candidate key, subset of candidate key, or right hand side is a non-prime attribute, right? If this condition exists, then we can say this B determined is a partial dependency, right? So here in this case you can see AB is a candidate key, but B is a part of candidate subset of candidate key, and it is determining non-prime attribute D. So in this case we can see B determine D, right? So this is the example of partial dependency. Same thing it is explained here in the terms of X, Y, and A. So A is a non-prime attribute, Y is basically a proper subset of candidate key, right? And X here, X is AB, Y is B, right? And A is C. That example I have took, right? So same thing. So first you have to find out the candidate key, then find out prime attribute, non-prime attribute, and then check for this condition whether my left hand side is having a proper subset of candidate key or not, and right hand side is a non-prime attribute or not. If this condition exists, then that function dependency is my partial dependency, and the relation is not in 2NF. Okay.
So we check the relation and then we convert it into 2NF. So first we check.
Yeah. So first we have to check whether it is in first NF or not. In order to be in 2NF, first it should be in 1NF, right? Once we have done that it is in 1NF, then we'll check for 2NF condition. To check that, we check whether it is having partial dependency or not. If it is there, we have to remove that partial dependency. But basically, we have to decompose that. So how to do that, I will discuss. Don't worry. Yeah.
Sure.
So just remember this condition for 2NF, and for 1NF, no MVA. Okay. Yeah. So here you can see is student table SID, S name, C name, right? So SID determines S name, SID determine S name, SID, C name combined determine S name. So SID, C name combined determine S name. So here you can see there is no MVA, right? There's no multi-attribute. So we can say it is in 1NF, right? So now to check whether it is in 2NF or not, we have to satisfy those conditions. So what is the key here? SID CNAME is a primary key, right? So SID CNAME is a primary key. So left hand side of an attribute, it is a key, right? Of this functional dependency. Then this is allowed in the 2NF. Only partial dependency is not allowed, right? So what is partial dependency? X comma A. X is basically a subset of candidate key and A is non-prime attribute, right? So here you can see SID determine S name. So our candidate key is SID and CNAME, right? Now this SID is a part of candidate key, right? So it is violating my 2NF condition because SNAME is a non-prime attribute here. So my this condition is getting satisfied means it is a partial dependency, right? So here partial dependency exists. So that's why we have to we need to decompose this table, right? In order to avoid the partial dependency. So how to do that? Once you identify like which of the functional dependencies are partial dependencies because it is violating the 2NF condition. So what you can do? Simply, oh, what happened? Yeah. So this functional dependency is violating. Now, in order to remove, in order to convert this 1NF to 2NF, what you can do? Simply take the closure of SID based on the functional dependencies set, that is F here. So if I take the closure of SID, I will get SID determines S name, right? So make this as a one table, that is R2. Say R1 or R2. So this is what we have done here. It is SID S name. So this is R1, right? And in order to satisfy the lossless join condition, or R2 must be that three conditions should get satisfied. So first one is R1 union R2 must be R. So these two attributes are covered. Now the attribute is remaining is CNAME, right? So in R2 CNAME will be there. Now to check for a second condition R1 intersection R2, there must be some common attribute, right? So you can see SID must be there because SID and CNAME is itself is a key, right? So here you can see SID CNAME itself is a key. So that's how we can decompose this table to 2NF. And here you can see only one functional dependency is applicable, that is SID determine S name. So by default SID is a primary key here, and here a combination is a primary key. Okay. Okay, anyone any doubt in this part? Partial dependency. So here also dependency will get preserved. Okay, 2NF. Dependency should get preserved. Okay, so one question. Suppose we have relation R. Okay, suppose this is a relation and it has no functional dependency, right? No functional dependency is there in this relation. So what should be my key here in this case if there is no functional dependencies? Yes, anyone?
SID.
Why? There is no functional dependency applicable to this particular table. Let us assume that.
So the whole tuple, like
Yeah. So the
every
combination
row
of
is
combination of all attribute will be my key, right? If there is no functional dependencies applicable to a table, then the combination of whole attribute is a key.
Right.
Okay,
Because SID is
right?
not unique. Yeah.
Yes. So that's the one thing you should remember. Okay, what happened? Hmm. So any doubt in 2NF? I will take a problem. Don't worry.
Sir, if it is the case, there is no key,
Hmm.
then that relation will be in 2NF, na?
No key, no functional dependency.
Sorry, no functional dependency.
Yeah, if there is no functional dependency, then the combination of all the attribute will be a key, right? So in
Yes,
that
sir.
case, it will be in BCNF. It will be in 1NF also. If this atomic 2NF also, 3NF also, BCNF also, right?
Sir, how?
because the condition for BCNF is left hand side of a primary key, sorry, any functional dependency must be a key, right? So you can see a combination of all the attribute is a key here.
Okay, sir.
You can also think like there is no
The,
functional
the
dependency.
quantity need not be a part of the combination in determining the key, no?
Sorry,
Because quantity need not be a part of the combination, no?
no.
In determining the
I am
key.
saying that let us assume that we don't have any functional dependencies applicable to this particular table. Then in that case, combination of all the attribute will be a key.
No, that's what I'm telling you. Quantity need not be part of the all the attributes. No, other than that one, all the things can be together can form a key for the attribute.
No, don't take this example. I'm saying
Uh,
in general, if there is no functional dependency applicable to any relation, then
mm,
combination of all the attribute will be a key, right? And it will be in
okay.
BCNF.
Okay.
Yeah. Okay. So yeah. So this is about partial dependency. Same example is there, right? Okay. So here you can see the key is SID and PID, right? The partial dependency is SID status, SID CD, because SID is a proper subset of candidate key, that is SID and PID, right? And it is determining non-prime attribute, right? These are the non-prime attribute. So it will lead to an violation of 2NF. It will be a partial dependency, right? So in order to remove this partial dependency, what we can do? We can simply take the closure of the left hand side of functional dependency and make it as a one table, right? So for example, if I take the combination of closure of SID, what will be the closure of SID based on these functional dependencies? SID give me CT, SID give me status, right? So it will be SID status comma CT, right? So just let us make this as one table, that is R1. So here you can see SID status CT. So what are the functional dependencies that are violating your condition? Just simply take the closure of that and make it as a one table. Okay, that's how we decompose the table. Okay, so here you can see that is one table, right? And all the three functional dependencies getting preserved here. This one, right? And the next table, that is R2. It will be my SID, PID, and quantity to preserve this functional dependency, right? And if you just apply those three conditions for decomposition, you can see SID is common attribute and SID will be a key for this particular relation R, right? So that's how we can decompose the table like 1NF to 2NF. Simply first find out the candidate key. Process is same for everything. Find out candidate key. Second, find out prime attribute, non-prime attribute. Third, apply those conditions. First, for 1NF, there should be no MVA. For 2NF, the left-hand side of functional dependency must not be a subset of candidate key, and right side should not be should not be a non-prime attribute. If it is there, then it is a partial dependency. And if this partial dependency exists, then simply take the closure of the left-hand side of a particular dependency and make it as a one table. Okay, so that's how we decompose 1NF to 2NF. Okay, anyone, any doubt? Okay, maybe I will take few example from practice assignment to discuss few example, then it will be more clear. First let me complete this 3NF, then we'll take few examples. Okay, so now what about third normal form? It should be in 1NF. For that it should be in 2NF, right? So it should be in 2NF, and for that it should be in 1NF, right? Then if it is in 2NF, then we can check for this particular thing. R should not contain transitive dependencies. What is transitive dependencies here?
Yes, for the B is going to see
Yeah,
here.
if A determine B and B determine C, then I can say A determine C, right? This is transitive dependency. but it is directly we can see based on looking at this functional dependency. But we have some more complex functional dependency and how to identify that, right? So in that case, what you can do, simply find out candidate key, find out prime attribute and non-prime attribute, and if in the functional dependency set non-prime attribute determines non-prime attribute, if this functional dependency exists, then we can say there is transitive dependency. Okay, here you can see every non-prime attributes of R is non-transitive dependent on every key of R. If this functional dependency exists, then it is a transitive dependency, and we can say it is not in 3NF, right? So first we have to check for whether this functional dependency, like non-prime attribute or non-prime attribute, is there or not in the functional dependency set. If it is there, then it is not in third normal form. Same it is mentioned here only. Alternatively, R is in 3NF if and only if each of the functional dependencies x minus a, at least one of the condition holds true. So x contains a, x contains a means AB determines a. So that is basically a trivial functional dependency, right? Or x is a super key. X is super key is basically a, it will give us all the attributes, so right? So directly it is in 3NF. And every element of x minus a set difference is a prime attribute, right? So suppose we have a b determine, say a b d, right? And if we take the difference, and if d is a prime attribute, then we can say it is in 3NF. Okay, but in short, just remember that first it should be in 2NF, and this condition should not be there, that is non-prime attribute determine non-prime attribute. So this is easy to remember. Okay, so same thing is mentioned here. Is in R every functional dependency x determine a associated with R either a subset of x that is trivial or x is super key of R, a is a part of some candidate key, right? Not just the super key. So relation is in 3NF, is naturally in 2NF, right? So that is transitive dependency. Okay, uh, let me summarize the concept. I will take few example that will be more clear. So there are different normal forms, right? So first one is 1NF. What is the condition for 1NF? No
No multi.
multi-valued attribute. For 2NF, no partial dependency, right? That is, if x determine a is there, x is a subset of candidate key and a is non-prime attribute. For 3NF, no transitive dependency, that is NPA determines NPA. If it is there, then it is not in 3NF, right? So it should not be there, and this one also should not be there in the 2NF. It will violates the normalized 2NF condition. Okay. Okay. First, tell me if this is clear. 1NF, 2NF, 3NF. What are the conditions? Just these conditions are
Yes, sir.
clear. Okay. Let me discuss few examples. It will be more clear. You need to practice for this because it will have more weightage in quiz too. About 50-55% you can assume. Okay. Which is the question? Question of Okay, is my screen visible? This question.
Not yet.
Practice assignment question number 1 and 2. Oh, what happened?
Sir, can you give the YouTube link?
Ah, it is there in the calendar. You can see.
Calendar is not there, sir.
I have updated it. You can check that.
Okay.
What happened to window? This one. Uh, hmm. Okay, this is visible. Week 6
Yes,
PA
sir.
question 1 and 2. Yeah. So for 1NF, the condition is no multi-valued attribute. For 2NF, no partial dependency. So what is partial dependency? X determine A. X is a subset of candidate key and A is non-prime attribute. Right? Then 3NF, there is no transitive dependency. What is transitive dependency? If non-prime attribute determine non-prime attribute, then we can say it is transitive dependency. And for BCNF, a simple thing, just check whether it is in 3NF or not. And one more condition is that every left hand side of every functional dependency must be a key, right? Left hand side is a key, right? That is BCNF. Okay, just remember these few things. You can solve any question on the week 6. Okay, this is only important. Now let us go for a first question. Consider relational schema R where domain is ABCD include
Sir,
atomic values.
can you repeat for BCNF conditions?
Yeah, for BCNF, first it should be in 3NF, right?
Okay.
And the second condition that is every left hand side of every functional dependency must be a key.
Every attribute.
See in this case, this must be a key, this must be key, this must be key. So left hand side of every functional dependency must be a key.
Okay. Sir.
Yeah. Then we can say it is in BCNF.
Okay.
So
Sir.
left hand side determines any attributes, and if it is key, then we can say it is in BCNF. But for that, it should be in 3NF. Okay.
Okay. Sir.
So now let us check
What is
this
expansion?
for this is
What is
question number
expansion
second
for
first.
BC and
We have
voice?
voice normal form. BOCY. It is there in the
Okay.
slides. Yeah. So yeah. So we have relation R. This is visible, right? Like attributes are visible, right?
Yes, sir.
Okay. So domain having atomic values only. So what does it mean?
One and
It is in 1NF, right? If R satisfies these functional dependencies, identify the correct statement. Now this relation R is 1NF. Now check whether it is in 2NF or not. Check whether it is in 2NF or not. How to check that?
First find candidate key.
Yes. So first find out candidate key. So what is candidate key here?
AB.
AB. Okay, wait. Uh, Let me take this in a different way. I will show you the. Hmm. Options. Okay. So we'll try to decompose this whole relation R. Okay. So as mentioned in the question, atomic values, it is in 1NF already, right? Now, so first step is find candidate key. Second step is what are the prime attribute and what are the non-prime attribute. Okay. So what is the candidate key here? Tell me how to find out. Hello. Yes. So first check which are the attribute which is not present right on right hand side of any functional dependency, right? So CD is present. So CD is present. F is present. A is present, and B is also present, right? Now in this case, what to do? Because all the attributes are present on the right hand side of any functional dependency. Then how to find out functional dependence? Oh, sorry, candidate key then.
Take the single attribute and find closer.
Yes. Then our conventional method, take the closure of all attribute A, B, C, D, right? E, F, and see whether it is the candidate key or not. Take the closure of A. What is the closure of A here? A only, right? Closure of B, B only. Closure of C, CB, right? And from CB, no. Closure of D, D only. Closure of
F.
E,
EF.
F, right? And from F, we are getting anything? No. Closure of F, no, right?
No.
So individual is not a candidate key. Now let us take for a combination AB, then AC, then AD, then AE, then AF. Because this question is very important. If you understand this, what I am doing, it will save your time in quizzes also to find out the candidate key. What is the closure of AB?
AB is a key. A, B, C, D, E, F.
A, B, C, D, E, right? And from
F.
E, I will get F. Okay, yes, A, B, C, D, E, F. So AB is the key, right? We have to check for other combinations also. AC, whether AC
C
is
is
there,
also. Yes,
yeah.
sir.
But from C, I will get B, right?
Yes, sir.
But if I
AB
get
is a key.
AB, already a key, right?
Yes.
So if AB is already present in the closure and that AB is already a key, so it will all, so AC will also give me all relation R, right? So AB and AC is also a key. Are you getting it? If in the closure of AC, if I am getting AB, then it will automatically give me all the attributes, na? Hello?
Yes, sir.
Yeah. Now take the closure of AD. AD closure. Uh, AD only, right?
Yes, sir.
AE,
E, F.
AEF, right? No. And that's it, right? So here AB, AC is a key. So like, are we done with the finding out candidate key or any possible also like combinations are there?
No, sir. We try out with other attribute combination also. Like.
Yeah.
Yes.
So AB and AC are the key here. Now let us check for BA, BC. Okay, BC we can check. BC only, right? Then BD, BE, BF. So what we have to do? What we have to do? Just see whether if in this closure AB or AC are coming, right? If we take the
B is
closure
a
of,
key.
sorry,
B is a key. B, F, A.
hmm, BE is a key,
Yes, sir.
because if I take the closure of BE, I will get BEF, and from BF I will get A, and if I get A and B, I will get the whole relation. Sorry, all the attributes, right? So B is also a key. BD is not present. BF is not present. So BF is there, right? BF is also a key. BF, right? It will give me BFA. So BFA will give me AB plus, that is all the attributes. So it is also a key, right? So till now we got AB, AC, BE, BF, right? Now can we check for CD, C, CF? We have to do that. CD, C, CF. There is no shortcut, but there is one trick. As of we know that if we get AB, AC, BE, BF, then it will be a key, right? So
Sir,
let us check. Huh?
sir, I do not understand how the BE is a key.
Yes, so if we take the closure of BE, what we will get? BE, right? From E, I will get F, right?
Right?
And from BF, I will get A, right?
Okay, okay, got it.
And
Yeah.
from AB, I will get all the attributes.
Mm-hmm. Understood.
That's it,
Thank you.
right?
Yeah.
Now, what about CD? Are we getting AB, AC, BE, BF in that?
CD is not the key, sir.
CD is not the key. CE, E, no, because EF, I will get EF only, right? Yeah. CE. From E, I will get F, and from C, I will get B, right? And BF is a key. So its closure will give me R. So C is also a key. What is CF then? CF, B, and BF is also a key, right? So it will also give me R. So CF is also a key. So check for DEDF. Now remaining are DEDF. Then one more is EF, right? The combination of two is over then. Then we have to go for combination of three. So D, 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 no D, right? DF, no, because not giving me A, B, C, D. Yeah. EF, EF will give me EF only, right? So that's it. Now, if we take the combination of this any key with any other attribute, it will be a super key, right?
Yes,
So
sir.
I don't need to check the combination of AB with any other attribute, combination of AC with any other attribute. So A, B, C, three should these three attributes should not be together, right? So that is done. Then B, E, F should not be together because it will give me already a key. Then what is the combination of three attributes are remaining? If we check C, D, E, E, F, yeah, I think that's it. That's are the key only. You can check for a combination of three attribute also. For example, C, A, B, C is done. C, D, E, right? Yeah, it will not give C, D, F. You can check. No, C, F, C is already key, so it will be a super key, right? Yeah. So these six are the key. Now just apply the okay. Now first tell me what are the prime attributes here. The attributes
A,
which are
B,
the part
C,
of candidate key. Yeah. So A, B, C,
E, F.
F. Only remaining is D, right?
Yes, sir.
Now check whether it is in 2NF or not, because it is already in 1NF. For 2NF, there should be no partial dependency. So in this case, subset of candidate key, and here A is non-prime attribute. Now see whether any functional dependence satisfying this condition or not. AB. So AB is the key, right? So we don't need to worry about this. E determine F.
F is a
Bo-
prime attribute. Then
E is also prime attribute, right? So this is also allowed. Subramanyam.
Yes,
Yeah,
sir.
yeah. Please mute. Okay. So this is also allowed because prime attribute determine prime attribute. This is allowed, right? BF determine A. BF is also candidate key. This is also allowed. Now C determine B. Tell me. C is also prime attribute. B is also prime attribute,
prime
right?
attribute.
Yeah. So my all the conditions for 2NF is getting satisfied because this functional dependency does not exist. That is partial dependency. So subset of candidate key not determining non-prime attribute. It means man, this relation is in 2NF also, right? Hello.
Yes, sir.
Right. Now for 3NF, just check whether non-prime attribute determine non-prime attribute is there or not.
No, no. It's in 3NF also.
Yeah, so it is in 3NF also. So it is in 2NF also, 3NF also. Now for BCNF, just check whether left hand side of any functional dependency is a key. So for this, it
Sir,
is a
by
key, right?
key is it? Sir, by key is it mean only candidate key or super key also?
No, super key also, any key. I said any key. Super key. Let us take
Okay.
super key because it will cover candidate key also, right? Super key
Yes.
determine anything, right? So AB is super key. This is allowed. BF is also allowed. But EF and CB, right? EF and CB. You can see left hand side is not a super key here, right? It's not a super key, right? So it is not into BCNF because violating this condition. Left hand side must be a key. In
Yes,
the
sir.
case of this, say suppose A, B, E determine F is there, then we can say it is allowed because AB is a key and combination of A, B, E is a super key, right? So this is allowed. But E determine F is only prime attribute determining prime attribute. This is not allowed in the 3NF. Sorry, BCNF. In BCNF is simpler. Just remember what happened. Okay. So BCNF, just left hand side is a key, that super key. That's we have to remember. So this is option is also correct, right? Anyone any doubt in this question? You have to follow this process for each and every problem in week 6. Here we are not getting the candidate key directly, looking at the functional dependency. That's why it took time. But yeah, but if it is the case, you have to follow this only. Okay. Say suppose I want to. Okay. Any doubt? Any question? Anyone? Okay. So suppose I want to decompose this into BCNF also because it is not in BCNF. Then how to do that? Anyone? I want to decompose. Okay, this is our correct option, right? R is not in BCNF. But how I want to decompose this relation R such that it should be in BCNF. So as I said, just check what are the conditions for BCNF. Left hand side of any functional dependency must be key. So this is key, this is allowed. This is also fine because BF is a candidate key. E determine F and C determine B is not allowed in BCNF because prime attribute determining non-prime attribute, right? So if these two functional dependencies are violating my BCNF condition, So what to do that? In this case, I want to decompose this into
Different
yeah,
relation.
yeah. So we need to decompose this relation R, right, into different relations so that it should be in BCNF. Then just simply take the closure of left hand side of the attribute, that is E. So take the closure of E, what I will get? EF only, right? Just take the closure of CB, what I will get? Sorry, CB only, right? Just make this as relation R1. This one is as R2. So this one is my R1, that is EF. This one is my R2, that is my CB, right? And what should be R3? Now tell me. If we have gone through week 5, you should be able to do that. How to find out R3 then? Such type of question you can expect. We will give R1, R2, find out R3, such that the decomposition is lossless. What is the condition for lossless decomposition?
Is it AD?
Sorry,
AD?
R3, AD. No. In order to satisfy the lossless decomposition, R1 union, in this case there are 3 tables, say more than 3. So R2 union R3 must be equals to R, right? So all the attribute must be covered. So C, B, E, F is already covered, right? So what are the remaining? A, B, C, D, E, F, right? So AD is remaining, but there must be some common attribute in order to satisfy the second condition, third condition, right? Tell me. And also these two functional dependency must be preserved. Okay, in the case of BCNF, it is not guaranteed, but we'll try to preserve that.
ADB.
ADB, right? So if I add B here, so A, B, D, right? So A, B, C, D, E, F, all the attributes are present. So my first condition is satisfied, right? Now, how to check for second condition? Take R1 intersection R2, right? In this case, take R2, R3, R2, R3 first. So any common is there? B, right? Either B is giving me R2 or R3.
No, sir.
So we cannot have B alone. Then
ABDF.
A, B, D, F, right? Because AD was remaining, right? And AB and BF are the keys, right? So it will cover all those things. So now take the okay. So now it is A, B, D, F. Now what is common? B only. Or here you can see what is common here. Take R2 union R3. In this case, only B is common. It will not give us any R2 or R3. Now take R1 intersection R3. What is common? F is common, right?
Yes, sir.
But will F give us the key? No, right?
No.
Yeah. So we have to find out such that the intersection should give us the key, right? So here you can see for this E is a key, for this which one? C is the key, right? The intersection of this must be a key there. So if I take A, D was remaining and EC, A, D, EC. Now check A, D, EC. here C is common, right? If I take the closure of C, we'll get CB, so R2, right? Now let us say R23 equals to R2 union R3. Okay, so have you tried the decomposition questions in week 5? Like R1, R2, R3 is there, like R4. Then how to check? Uh,
Yes, sir.
so no issue, yeah. So now R2, R3 will be A, D, B, C, E. Now R2, 3 intersection R1. So it will be, right. It will give me R1. My first condition getting satisfied, and this decomposition is in lossless decomposition, right? Okay, this is how we have to do if we want to decompose
Sir,
into BCNF.
sir, can you please explain again how to find this R3? We have to hit and trial, or is there any other method?
So yeah, if you want to look for lossless decompose, what are the conditions? From conditions only that we can directly say. So first one is R1 union R2 union R3 must be equals to R, right? So the remaining attribute must be present in the R3, right? That is for sure, right? That is AD, right?
Yes, sir.
Satisfy first condition. Now, if you observe second and third condition, what I said earlier, there must be some common attribute, and that common attribute must be a key, right? At the start of session, I have discussed one question. In that, I have said,
Yes, sir.
yeah, because we have two conditions, right? So there is very good question in quiz 2 mock. In that, you can solve that, but yeah. The second condition is R1 intersection R2 should not be an empty set, and R1 intersection R2 should give me R1 or R2. If you look at these two conditions together, what this infer that there must be some common attribute, right? And that common attribute must be a key of R1 and R2, either R1 or R2, right?
Yes.
Yeah. So I already know the key for this R1 and R2. So I just simply try to put first ADE, right? So ADE will give me this EF, right? Now ADEF, but I don't have any common attribute between R2 and this R1 union R3. So I will try to put C also here, right? But in this case, our functional dependency is not preserved here. So this is not a good
Sir,
condition.
I understand till ADE. Then why we put C also? That I didn't understand.
Yeah. So if you take ADE and check for first condition, that is R1 intersection R3. So in this case, E is a common attribute, right?
Yes, sir.
Yeah. And if you take the closure of E, we'll get
R1.
R1, right? But now to check for R2 also, what we have to do, say R1 3 equals to R1 union R3. That is E, F, A, D,
A,
C.
D.
Now check R1 3 intersection R2. Is there any
C.
common? C is there, right?
Yes, sir.
Yeah. Oh, no, C is not there now. We are just considering ADE only
Okay,
initially,
okay.
right?
Oh, yes.
Yeah.
Yes, yes.
Because there is no
ADE.
common, right? So in this case, it will be a lossy. So we need to include this key also here.
Okay.
Yeah. So wait,
Then
this
maybe
is
the remaining attribute and the key of the other relations.
yes. So in this case only we have tried this, but there are a few other cases you will directly get based on our functional dependencies, because here it is not getting preserved. So this is preserved, this is preserved, this function dependence is not preserved, but it is still in BCNF. That's what I have discussed. We can get BCNF, but function dependency may not get preserved. For 3NF, dependencies will get preserved. Okay, so you can try out this. One more question is there in the practice assignment. 4NF. Yes. Practice assignment question number 10. You try to solve that. Okay. Because in this way only I can discuss that question. It will take around half an hour, but by options you can directly go through it, but your concept will be get clear if you solve like this. In question number 10, you have to follow the same procedure what I have discussed, but there are different conditions also, right? So that will be a good example if you try to solve by your own. Okay. So question number 10, please try to solve that. Okay. Practice assignment question number 10. If you get that correct, you will get 90% of the question correct in the week 6 based on these normal forms. Question number 10, try to do that. Don't look at the solution. There's a different method in solution, but try what I have discussed today. Okay. So it's about normal forms. Now let's go back to the slides. So we have discussed 1NF, 2NF, 3NF, BCNF also. Not from the slide, but yeah. So how to decompose to 3NF, right? So here you can see. Sorry. So there is always a lossless join. Dependency preserving decomposition into 3NF. Okay. So till 3NF we can preserve the dependency. And this is the condition for 3NF. Please try to remember all the conditions for 1NF, 2NF, 3NF, BCNF. Okay. Yeah. So here it is not mentioned that okay X is super key, because if X is super key, it is in BCNF, means it is already in 3NF, right? A is a part of some candidate key. A is a part of some candidate key. If it is a prime attribute, right, this is allowed. So what I am saying, just check for non-prime attribute determining non-prime attribute, right? It will cover all the above three conditions, right? If it is there, then it is not in 3NF. It will violate the condition for 3NF, that is transitive dependency, right? Transitive dependency. Same thing. You have to check for multiple things instead of just check for one thing, because it is inferred from this thing only. We are saying that A is a part of some candidate key, means A is a prime attribute. If it is there, it is allowed. What is not allowed? If A is non-prime attribute. That's it here, right? If A is non-prime attribute and it is determined non-prime attribute, simply it will violate the 3NF condition. So relation is in 3NF, is naturally is in 2NF, right? Yeah, so testing for 3NF has been shown. Okay, there is algorithm to how to find out the 3NF decomposition and BCNF. So in the lecture, what we have discussed, that first find out the canonical cover. Okay, so this relation R, functional dependency set is given to us, and we have to decompose into 3NF. Okay, so the first thing is that our method, find out the candidate key, find out prime attribute, non-prime attribute. 1NF is there, check for 2NF. Okay, if few conditions are violating, then take the closure of left hand side and make it as a one table, and check for a 3NF condition again. If few conditions are violating, take the closure and decompose it further. So that thing is a one method. Or directly, if you want to do, what you can do, first find out the canonical cover. So concept of canonical cover is discussed in the week 5. Canonical cover, right? So this is canonical cover. Element functional dependencies, it is in canonical cover of FCs for F. The create a relation Ri xi for each of the functional dependencies. Once you calculate canonical cover, say AB determines C, then say D determine E, like this. If this is a canonical cover, what you can do, simply make this table, right? DE like this in FC, right? That will be give us the 3NF condition, right? But what is canonical cover? Anyone? Like anyone know how to find out canonical
Minimum,
cover?
sir. Yes, sir.
Yes.
Yes, sir.
Yes. Tell me.
Sir, first, all the attribute in the right side we have to write in single, like A determined CD. We have to write like this: A determined C or A determined D.
Right.
Then
Then
remove any extraneous attribute
Ah.
is
So
present
first,
in functional dependency.
just follow this and then remove some extraneous attribute, right? Extraneous attribute. Now, extraneous attribute we can do from two cases, like whether from a left hand side or right hand side, right? Right. So you have already decomposed this into A determine C, A determine D also, right? So suppose if A, B determine C, I have to check whether A is extraneous or B is extraneous, right? To get the C. And how to check whether which attribute is extraneous? Yes, anyone tell me?
So find the closer or A or B separately. If we are getting C,
Hmm?
without, then
Yes.
other one is the extraneous attribute.
If we want to see whether A is extraneous or not, then what we do? Take the closure of B, right? If you are getting C, then A is extraneous. Right? If you are not getting C, then A is not extraneous. Take the closure itself. If you are getting C, then extraneous, right? Hello. Once you remove the extraneous attribute, then you have to remove
Your
functional
voice is
dependency,
breaking, sir.
right? Hello.
Your
Hello, am
voice
I
is
audible?
breaking. ಇಲ್ಲ ಮಾತಾಡಲ್ಲ.
Okay, so is it for everyone or hello?
Yes, sir, for everyone.
It
Sometimes
was
it's breaking,
breaking.
sometimes it's
Now
clear.
I think it is
Okay, maybe
okay.
my
Let's give it a try for some time, then we will come back to you.
hello.
Yeah, yes, sir. Go ahead, please.
Now audible clearly.
Yes, sir.
Yes, sir.
Okay. So once you find out the extraneous attribute, the next step is to eliminate redundant functional dependencies. So what is redundant functional dependencies? Just tell me, anyone.
Sir, we look for the all three axiom for the FDs like transitive, or then remove the redundant.
Yeah. So suppose A determine B, B determine C, and C determine A determine C is there. So we remove this functional dependency because we are already getting this from transitive, right? So once you find out remove extraneous attribute and remove redundant functional dependency, you will get a canonical cover. So once you get a canonical cover, you can simply create a relation Ri xi, that is for each functional dependencies like this, okay, and make it as a relation R. If key k of R does not occur in any of the relation, create one more relation Ri equals to k. So this condition is very important, okay. So as I said, practice assignment question number 10. Try to follow whatever I discussed right now method, and this condition is applicable there. Okay. So if the key of R does not occur in any of the relation Ri, one more relation Ri should be equals to k. Okay. So for example, in the previous example only, we have R1, R2, R3, R3 only, right? So suppose we have EF, CD, and we are having so suppose A, B, D, right? And it is not giving the lossless decomposition. So what I can do, I can add one more relation R4 such that it should be a key, right?
Key for all the relation R or any of
R,
these.
R. Very good
Okay.
question. Key for R, main relation R. So yes, if we are not getting like sometimes it's possible that our decomposition is correct, R2, R1, R2, R3, all the functional dependencies are getting satisfied, but it is lossless, right? All functional dependencies are preserved, but it is lossless. sorry, it is lossy. So in order to make it lossless, what we can do, we can add one more relation such that it should have all the attributes of key, right? So please try to solve practice assignment question number 10. It will cover all this concept. Okay. So in this question there will be two candidate key. If we use any one of the candidate key, you will get the decomposed relation as lossless, right? And one of the candidate key is mentioned in the correct option. Okay. So this question is very important. Try to solve that. I will solve in the next lecture, in the next session, if you are not able to do that. Okay. So this is about 3ANF decomposition. So algorithm, you can just watch the lecture, go through it. Same thing is there. Yeah. So upon decomposition, each relation schema Ri is in 3NF, decomposition, dependency preserving, and lossless also, right? So till 3NF, we can have a dependency preserved and lossless join. Now 3NF decomposition is, now let us take this example. We have relation customer bank branch having attribute customer ID, employee ID. This is a candidate key because it's underlined, right? Branch name and type. The functional dependencies for this relation schema are like this only. So first we need to compute canonical cover. So here in this case, like we have to see whether customer ID, employee ID, any attribute is extraneous, or in this case customer ID or branch name is extraneous. Because for B it is atomic, right? It's only one attributes are there, so we don't need to check for extraneous. So in the case of A and C, we need to check whether any one of the attribute is extraneous or not, right? So here if you see branch name is extraneous, right, in right hand side of the first functional dependency here in this case. So how to check? Okay, so we have discussed about if how to check extraneous attribute. I should reduce the thickness. Extraneous attribute on left hand side. So left hand side is simple, right? A, B determine C. Take the closure of A. If A, C is there, B is extraneous. Otherwise, take the closure of B. If C is there in the B closure, A is extraneous. But how to check in the case of right hand side? Does anyone tell me?
Take the A closer.
A closure.
Customer ID closer.
Tell me. Just take the closure of left hand side of this functional dependency and don't include this functional dependency. Remove this functional dependency. Okay. So we are remaining with these two functional dependencies. So if I take the closure of customer ID and employee ID, what I will get? CID. I will write down EID closure. What I will get? Don't consider first functional dependency because for that only we are checking, right? Based on other two functional dependency.
So CID EID itself.
CID
EID branch name.
Branch name, right?
Employee ID
So
also. Achha.
employee ID also, right? So in the closure of employee ID and CID, we are already getting the branch name, right? So this is extraneous then, right? We can simply remove this, right? Hello?
Yes, sir.
So just take the closure of left hand side of those functional dependencies for which we are checking for the right hand side and see whether that attribute is there or not in the closure. In this case, branch name is there, so simply we can remove that, right? If in the case of branch name it is type, then we can remove type because type is extraneous in that case, right? And if both branch name and type are present in the closure, say suppose here I will add type also. In this case, both branch name and type will be present. Then whole this functional dependency is redundant, right? So we can remove this functional dependency. Are you getting my point? Hello.
Yes, sir.
So that's how we calculate canonical cover. Sorry, extraneous attribute. Then this is clear. No other attribute is extraneous, so we get this is a canonical curve. If we remove branch name, these are the functional dependencies. Now, according to algorithm, what we said, for the loop generated following 3NF schemas, right? So just simply create one relation R1 for this, R2 for this, R3 for this. So that's what we have done. Observe that candidates contain a candidate key of original schema, so no further relation schema needs to be added because it already key is there. So that's why it will give us the lossless decomposition, right? Detect schemas such as employee ID, branch name, which are okay. The result is simplified. Okay. So employee ID and branch name, which are subset of other schemas, right? So here you can see branch name, employee ID, branch name, employee ID, right? So this getting repeated. So we can simply remove this because it's getting a subset of this particular relation. So there will be two relation. This one is R1, this one is R2. All the attributes are there and the conditions are getting satisfied for lossless decomposition. Okay. So this is the one method to decompose the relation R into 3NF using canonical cover. Once you get 3NF, you can check for BCNF also, right?
Sir, 3NF is dependency preserving and lossless to both.
Yes,
But
yes.
in BCNF, the it's may or may not be functional
Yeah.
dependency preserving. So why we prefer BCNF over 3NF?
No, we are not preferring. Okay. So in this case, suppose we want say dependencies does not matter in that case, but we want to decompose the table further, right? So in that case, we will go for BCNF.
So, sir, what are the cases when we go for 3NF and when we go for BCNF?
So till 3NF, like what we can do, we can avoid all the anomalies that cause due to functional dependency, insertion, deletion, right? So it depends on the case study and problem statement or database schema we are given to us. So generally we try to achieve 3NF because it will normalize the database, right? All the functional dependency will get preserved. So functional dependencies are preserved. So that's the number one condition we want, and it is lossless also, right? Yeah. If you go for BCNF, then it will lead to a mode table, right?
Yes, sir.
Yeah. So that's the case.
Sir, in what real life scenario when BCNF is required? If 3NF is already there, why the need of BCNF? That's what I was.
Okay. So suppose in any of the case like that, functional dependencies like does not matter much. Okay. So like preservation is does not required, but the table is getting more bulky. Say we have a lot more attributes, right? And if it's causing some anomalies to like error in updating the data or something, right? So in that case, we can go for BCNF. So it depends on the case study, not exactly in this case only, but it depends.
Okay, sir.
Yeah. So this is the one thing like what happened. Uh, I think YouTube streaming got stopped. Am I audible? Hello.
Yes, sir.
Yes, sir.
Okay, I will upload the later part of the video. No issue. So yeah. So this is the one method. Like find out the canonical cover, then make relations for each of the functional dependencies and see whether there is duplicacy of schemas or not, and remove that. Okay. Now if we go by our first method in this case, so what is the candidate key here based on these functional dependencies? It's already given, right? This one. So customer ID, employee ID is the primary key, right? So what are the prime attributes here?
Customer ID, employee ID.
Yeah, this is prime attribute, this is prime attribute, NPA, NPA. So customer ID, employee ID. So this is the left hand side is the key. So no issue. This is okay. You don't need to check. Then employee ID, branch name. Employee ID, it's a prime attribute determining non-prime attribute. So what is this? Tell me. We have discussed. Employee ID is basically a subset of candidate key, right? And this is non-prime attribute. So it's what?
Partial dependence.
Yeah, it is partial dependency. It means it violates 2NF condition, right?
Yes, sir.
Yeah. What is customer ID, branch name? So customer ID is PA. So PA, it is NPA determining employee ID is also prime attribute, right? So this condition is allowed. Combination of prime attribute plus non-prime attribute determining prime attribute. Okay, this is allowed. So only we have issue with this thing. Prime attribute determining non-prime attribute. It will violate the 2NF condition. Means this relation is in 1NF only, not in 2NF, right? So now, how to decompose into 2NF?
And find closer for this employee ID and
That's it. So closer for employee ID is
employee ID branch name.
employee ID and branch name only, right?
Yes.
Any other?
No, sir.
Employee ID and branch name. Okay, so branch name, customer ID, yeah. So just make it as a one relation R1, right? And then what will be R2? Employee ID, branch name, customer ID, type, and then employee ID, because employee ID is the key. This is my R2. So R1, R2 is lossless condition now, and dependency preserving also. Employee ID, customer ID is there, and this is a mining type. This is valid, and employee ID branch. Employee ID branch is there, customer ID branch, and employee ID. Okay, that we have to check. So that's the thing, right? I think same thing we are getting here also, but one more relation is to be there, right? So there are multiple decomposition also possible. Okay. Yeah. So it's a practice problem you can try out. In week 5, I guess there is a practice problem where we need to check like R1 is R is decomposed into R1, R2, R3, R4 like this, and see whether it is lossy or lossless. So please try those problem. Okay. If you try that problem, then you come back to week 6. Decompose all the following schemas to 3 in the following steps. Compute all keys. Yeah. So by using canonical cover method, find out solve this all the questions. You can try it out. Decomposition. Yes. So this is BCNF condition. Relation R is in BCNF with respect to F. All the functional dependencies F loss in the form of A alpha determine beta. Okay, at least one of the following condition holds true. There are only two conditions. Alpha determines beta, which is trivial function dependency, right? And here alpha is a super key of R. So that's what I said. If X determine A, X is the left hand side of super key, right? So left hand side of any functional dependency is a super key. Then we can say that is allowed in 3 BCNF condition. So in BCNF only one condition is there. So left hand side must be a key, right? That's it. So it is easy to remember this BCNF condition. Decomposition, yeah, this is the algorithm you can find out. Testing for BCNF. Okay, try to follow this and then just try to follow like what we have discussed today, so you will get the same output. Yeah, so here is one example. We have relation R, functional dependencies. We are decomposing R1, R2, R3, right? So this AB is preserved here, BC is preserved, and CD is also preserved. Now we have to check whether DA is preserved or not, right? So how to do that? This is about dependency preservation. I think same slide is there in the week 5 also.
Yes, sir.
Yeah. So how to check dependency preserving or not? So first find out F1, F2, F3 based on R1, R2, R3, means all the possible functional dependencies that is applicable to R1. F2 means all the possible functional dependencies that is applicable to R2, and F3 is all the possible functional dependencies applicable to R3. Take the closure of C based on this parent functional dependency and find out what is applicable functional dependency. Take the closure of D based on the parent functional dependencies, okay, and find out what are the applicable functional dependencies, right? So suppose in R3 we have A, C, D like this, right? And for example, you find out C determinant is only one in here, but just if you take the closure of D, you will get some E, F, A, C. So what you can say, D determines AC also, right? So I'm just giving one example. If in the closure of D plus, it is E, F, A, C, right? So what does it mean? D determine E, D determine F, D determine A, D determine C also, right? And D determine combination of AC, E, ACF, right? So these are all are the possible functional dependencies, right? But in the case of R3, only ACD is there, so we'll consider only where ACD is applicable, right? So based on the parent functional dependency, take the closure of each attribute and try to find out which is applicable to this R3. So here we have find out A, AB, B, BA, okay? So these three are functional dependencies. Union of all the three functional dependencies, F1, F2, F3, say F dash, and check whether this functional dependency is preserved or not using F dash. So just take the closure of D plus based on the F dash, okay? If it is A is there, then we can say D is preserved, A is preserved, okay? So this is the case for functional dependencies getting preserved. Same is a different method to follow. You can try it out. BCNF algorithm. Same thing. Create R1 AB, create R2. Here you can see if for all functional dependencies A determine B in F plus, check A is a super key or not, right? By using attribute closure. If not, then choose a functional dependency F that breaks BCNF rule, say that A determine B. Create R1 AB, right? Just take the closure of AB, then remaining attributes from R minus B minus A, right? So note that R intersection A and A should give AB equals, so this is lossless decomposition, right? This is what I have discussed during the first question, like question number 2 that we have discussed for week 5, for week 6, and repeat for R1, R2, right? Another algorithm you can find out. Yeah, okay, so BCNF decompose dependency preserving. Here you can see it is not always possible to get BCNF decomposition, that is dependency preserving. That's what I'm saying. We may or may not get preserved, right? Dependency may not get preserved. See, for example, we have relation R, JK determine L, L determine K, two candidates key JK and JL. R is not in BCNF. Any decomposition of R will fail to preserve this. Right? This implies that testing of JK determine L requires join. Right? It's not always possible to get BCNF decomposition, but 3NF, yeah, it should be there. Dependency must be preserved. So practice problem, just try to do that, and comparison you can go through it. So there are lots of practice problem in the week 5 and week 6. So please try to attempt that, okay? And if you have any doubt in solving those, or after solving, if you want to check your answer, just post it on Discord. You can tag me, okay? So yeah. So to sum up this, so this normal form, we have discussed 1NF, 2NF, 3NF, and BCNF, right? So for 1NF, no multi-valued attribute. For 2NF, no partial dependency. For 3NF, no transitive dependency. And for BCNF, left hand side of any functional dependency must be a key, right? Every functional dependency must be a key. So these are the 4 conditions, like 4 normal forms. If the relation is in BCNF, it means it is 3NF, 2NF, 1NF also, right? So that's the case. So just try to solve all the practice problems, graded questions also based on the normal forms, okay? Just follow this, what I have discussed today, you will be able to solve the problems. So like anyone, any doubt in 1NF, 2NF, 3NF, BCNF, you can ask. Next session we will discuss about MVD and 4NF.
Sir,
Yes,
in many of the assignment question, there are the composed relation R1, R2, R3, and we have to find out the it is in BCNF or not, and how to do that question, sir.
okay, suppose in the question R1, R2, R3 is given.
Then we have to find separately R1 is in BCNF or R2 is in BCNF.
Yes, yes. So every decomposed relation must be in BCNF. Okay.
Then, sir, we consider the given FDs for the relation R.
Yes, given FDs for relation R. Say for example, let me share. So this is question number 10, right? I'm talking about. Try to solve this. So here we need to find out from among the decomposition given, identify one that is BCNF, right? So we have 4 options. So each and every decomposed relation must be in BCNF, right? With respect to this particular thing. Because here I think it is easy. Just find out the candidate key and see whether it is there or not, left hand side or not. If right,
Yes.
this question is easy if you go for option elimination method one by one, but I will recommend you try to solve this. Don't go through option, just take this much question and try to decompose into BCNF like what I have discussed today. So you will be getting different answers, and those will be also be correct. Because in this question the decomposition, like how we decompose, even after decomposition functional dependency is not getting preserved. Then we need to add one more relation which will be a candidate key. Okay, so all this concept is covered in this question. So this question is about MVD, so MVD will discuss, but please practice about 1NF 2NF. For such cases, like here you can see, like consideration R, identify possible set, function dependent R, such that R is in BCNF. So what is the condition for BCNF? The left hand side must be a key, right? That's it. So you can see AB will give me ACDE. So AB is a key. Here AB will give me ABCDE. So AB is a key here. But we determine E is not satisfying my condition, right? Because B is not a key here. So this will not be true. Similarly, C and D will not be true. Right? So only option 1 is correct.
Okay, sir.
Yeah. So try to solve all the question based on 1NF, 2NF, 3NF, BCNF. Okay. So yeah, that's it. You will be able to solve all the question if you just follow those 3 simple steps. Find out candidate key, find out prime attribute, non-prime attribute. First you have done with this, then check for 2NF partial dependency. That is left hand side is a subset of candidate key determining non-prime attribute. If it is there, then take the closure of left hand side, add it as a one column. Check for 3NF, that is transitive dependency, non-prime attribute determining non-prime attribute. If it is there, then try to remove that. For that, just take the closure of left hand side of the functional dependency and they make it as a separate relation. So this is the simple process. So for that you need to do practice. That's it. Okay. Yeah, that's it from my side. You can ask if you have any question. Okay, thank you then. Yeah, I will close the session.
Thank you, sir.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you everyone. Bye bye.